Determine the force in members JI, JD, and DE of the truss. State if the members are in tension or compression. To begin, first of all, let's determine where our cut in the truss is going to be, because we're going to use method of section, and I'm thinking somewhere along here between GI and now we can determine which side of the truss is going to be most appropriate to solve this problem, and I think right hand side would be the easiest since has lower amount or lesser amount of reaction forces. So therefore we only need to determine our external reaction force at the roller G, and we can ignore AY and AX. Okay, to begin, we're going to take a moment about the point A. To find a solution for GY, it's going to be two external reaction forces of 15K counterclockwise. First one is 3 meters away and second is 6 meters away. Then we have clockwise 30 kilonewtons, 9 meters away. Then we have 20 kilonewtons, 12 meters away. 10 counterclockwise, 15 meters away. And finally, clockwise 5 kilonewtons, 18 meters away. And we have counterclockwise GY 18 meters away as well, all equals to 0. Solution for GI comes up to be 49.17 kilonewton, vector pointing upwards. Now we can draw the free body diagram of our right hand side we're going to solve for. So we'll have G and member going all the way till I from G. At G we have two reaction forces, external reaction forces, you can say. One is 5 kilonewton and the other one is 49.7 kilonewton. At point H, we have one external at 10 kilonewton, and at I, we have another one 20 kilonewton. At I, we also have force in member JI. Similarly, we're going to have a diagonal member all the way till E, and at E, we're going to have reaction force from member DE, and another one for member JE, and our imaginary point in this case will be J, And before we proceed, we also need to find our angles here so that we don't have to worry about them later on. So our first angle will be angle theta, which is going to be tan 1 meter divided by 3 meters. This comes up to be 18.43 degrees. Then our angle beta for JE, it's going to be 2 meters divided by 3, and this angle is 33.69 degrees. Now we can solve for this problem. Okay, to begin, let's take a moment about the point J. In order to find our solution for member D, we're going to have external reaction force of 20 kilonewton in clockwise direction, 3 meters away from J, clockwise 10 kilonewton, 6 meters away, clockwise 5 kilonewton, 9 meters away, counterclockwise 49.17 kilonewton, 9 meters away, and then the horizontal component of DE in clockwise direction, therefore it's going to be cos 18.43 degrees times member DE, all equals to 0. Solve for force in member DE, we get our solution as while calculating on the calculator, I just noticed that we did not include the moment arms distance here for our horizontal member of force DE. So this member is going to be 2 meters away, all equals to 0. And one more thing we missed is our vertical component. So this is going to be positive sine 18.43 degrees times force member DE and times the distance away, and in this case it's going to be 3 meters, all equals to 0. And now finally we can solve for force member D, and our solution comes up to be 97.52 degrees. Pardon me. kilonewton. Now we can sum the forces in x direction, pardon me, y direction in order to solve for force member JE. We're going to have downward direction forces 20, 10, and 5. And downward vertical component of force DE. And then vertical component of force J. And finally our external direction force from the roller, 49.17 kilonewton, all equals to 0. Solve for force EJ, we get our solution as. So our force EJ is going to be 27.88 kilonewton. Now we can sum the forces in x direction in order to find our solution for force JI. It's going to be simply horizontal component of force EJ and DE. So we need to have positive force IJ, we're going to have horizontal component of EJ and DE. Both are negative, all equals to 0. Solving for IJ, we get our solution as 115.72 kilonewton. Now we can continue to solve for JD. To solve for JD, there are a couple of ways. We can either make assumption, but I do not want to make any assumption because we don't have symmetrical external forces on each side of the truss. However, if you look at textbook solution, they're assuming that both sides are symmetrical, and in doing so, they're assuming they have already found the solution for JK, CD, and CJ. But I feel it's going to be different values for the members. Therefore, I'm going to make another cut between KJ, CJ, and CD to determine the values for members CJ and CD in order to find our solution for member JD. Okay, so our angles are symmetrical because our truss structure is similar on both sides. Therefore, we can have our angle theta and our angle beta. but everything else should be different. To solve it, I know I said we don't need AY, but looks like we do it because we made another cut, and this means this time we're going to use our left hand side of the truss to get the forces in the members we require. Or we could have done left hand side as well, but it's a little bit more work, so I don't want to do extra work if I don't have to. So let's draw the free body diagram of the right hand side. And even before we do that, let's find the solution for AY. So it's simply going to be sum of the forces in Y direction. So we're going to have negative 15 kilonewton to negative 5 kilonewtons. So it's basically 10 kilonewton. Oh, and pardon me, we have two negative 15 as well, so therefore it'll be negative 30, another negative 30 kilonewton, and then adding negative 20 and negative 10, we get negative 30 kilonewton. And then we have positive GY, which we found to be 49.17 kilonewton. And we have our positive AY, all equals to 0. Solve for AY, we get a solution as 50.83 kilonewton. And we know our AX is going to be 0 because when we do visual inspection, there isn't any external force acting on this truss. Okay, now that we have done that, let's draw the free body diagram for the right hand side. So we're going to have point A all the way till point K. And then we're going to have 15 kilonewton, another 15 at L, and 5 kilonewton at A. Then we have another reaction from the pin, 50.83 kilonewton. Then we have our truss going downwards or at diagonal and goes all the way to joint C. At C we're going to have two force members, CJ and CD. And then we have our external, oh, pardon me, force from member KJ. And we already found our angles, so our angle theta and angle beta. And using the same idea we did before, we're gonna take our moment about the point J, which is imaginary in this scenario. When we take moment about the point J, we're gonna have horizontal and vertical component of CD. Both are counterclockwise. Then we have counterclockwise two external reaction forces of 15 kilonewton. One is 3 meters away and the second one is 6 meters away. We have another one 5 kilonewton counterclockwise, 9 meters away. And then we have clockwise our AY 50.83 kilonewton, 9 meters away, all equals to 0. We get our solution as 97.52 kilonewton. Looks like textbook assumption that both sides of the member JD have symmetrical forces is correct. Therefore, now we can simply use method of joints at joint D to find our solution for member JD. At joint D, we have two diagonal forces. Force DE and force CD. And then lastly, our force from member JD, which is unknown. And we're gonna have our angle thetas here. Okay, so now to solve for JD, we can sum the forces in y direction, and it should get us our solution for member JD. So we're gonna have positive force for member JD or DJ, and we're gonna need vertical component of member DE and CD. Both are symmetrical, therefore we can simply times 2 one equation, all equals to 0. Solving for force DJ, we get a solution as negative 61.73 kilonewton. Because we get our solution in negative, this means we assumed our vector direction to be in the wrong direction. Switching the vector, get our solution in positive, and also this vector tells us that this member is in compression. Now we can go back to our other vectors and also determine if they are in compression or tension. So we needed GI and DE. So our member DE is in tension because our vector is going away, and our member IJ or JI is in compression.